Hey everybody, welcome back, and this is going to be the third and last video that we do on optimization. Now, you probably noticed that the previous two videos were a lot of just us solving the problem, and many times that's kind of what's needed here for these optimization problems. You've got to see a few of them to really get the experience you need to solve them even semi-reliably. So here we're going to go with yet another example, and this one's a little bit more complicated. There are more things going on, and yeah, let's just jump right into it right now. So here we got a boat escaping a bunch of zombies, because Chapter 5 is zombies, like we've talked about. So currently, hidden in the shacks on the water's edge, your group of zombie apocalypse survivors must make the zombie biathlon, running and swimming and cardio. Okay, that's actually a triathlon, but let's not lose the point here. To get to an abandoned boat and anchored offshore. Due to the rocky topography, it's impossible to access the water directly. Oops, sorry. You must run at least 5 meters from the shack down the shore before you start swimming. The boat is located 60 meters downshore from your location and 40 meters offshore perpendicular to the shoreline. If you run at 6 and swim at 0.9 meters per second, how much should you run and swim if you want to reach the boat as fast as possible? Okay, so there's going to be well, this is what's going to make this a little bit more difficult. There are two distances we need to deal with, and two different rates for those distances. We have, to start off with, we've got running, and the speed for running is 6 meters per second, and we have to run for 55. We'll talk about that in a minute. And then we have 0.9 meters per second for swimming, and we have to swim at least 40 meters, maybe more. And with a combination of running and swimming, we'll get to that boat. So we must combine two different distances. We have running and swimming distances, and each of those distances will be covered at a different rate, like we said before. So we just need to figure out those distances, and then we're going to let our handy formula, distance is equal to rate multiplied by time, and that will be our overarching mathematical model here. So let's see what we got here. We've got a diagram of the situation that's going to be helpful. This one's a pretty colorful one. We're going to run a distance. So we have to run at least this 5 meters right here. Let me use a different color for you. We've got to run at least 5 meters here, plus some other amount. And then we have to swim another distance, maybe diagonally, maybe not, but we have to swim that distance there. So notice the right triangle in the diagram. You wouldn't know about this right triangle unless you've done a few of these problems, but that right triangle does exist. The Pythagorean theorem will be used as a secondary equation, because remember, what we're really interested in here, or one of the things we're really interested in here, is this distance right over here. So we're going to mark that unknown leg with the x. Now the x, remember, that is the distance that we're going to swim. So the total distance to run in terms of x. Actually, when I'm thinking about this, it might be easier if we make our x this distance right down over here. So let's make this our x over here. So what's the total distance to run in terms of x? Now the entire distance here from left to right is 60 meters. We have to run all of it except for this 5 right here. Or I'm sorry, for this x distance right here. So this distance right here, this is going to be 60 minus x. That's how much we have to run. We have to make sure that 60 minus x is also greater than 5 because of this 5 meter bit right here. This 5 meters means that I've got to make sure that 60 minus x is going to be greater than 5. Now the next question is, how much do we have to swim? Now what about the total distance that we need to swim? How much do we need to swim? Okay, for that one, now that I have the x there, you see that I have a right triangle. The distance we need to swim is just the hypotenuse of this right triangle. So there's a other mathematical model we're going to need to use. It's a hypotenuse of the right triangle. Well, that hypotenuse is just the square root of x squared plus 40 squared. So that's the distance that we need to swim. Okay, using the distance equals rate times time equations, how long will it take to run in terms of x? Let's figure that out right now. So for the run, the distance is equal to rate multiplied by time, which means that the distance 60 minus x is going to be equal to 60 t. Sorry, 6t. We're running at 6 meters per second. So 6 meters per second for the rate here, and times the time. Now, to get the time, we're just going to solve that. So the time that we're going to run is just going to be 60 minus x on 6. Now let's do the same thing for swimming. And if we're swimming and distance is again equal to rate times time, then we get that the square root of x squared plus 40 squared is equal to 0.9 t. Again, the speed that we're swimming is 0.9 meters per second. Which means that the time, how long we're going to swim, is going to be x squared plus 40 squared over 0.9. So those two quantities together, 60 minus x over 6 and x squared plus 40 squared over 0.9, those two quantities together will give us a total time we're going to need to reach that boat. And that's going to be just the sum of those two times. Now we can simplify that a little bit. Actually, let's just zoom in a little bit here. We can simplify that to be 10 minus 1/6 x plus 10 over 9 multiplied by the quantity of x squared plus 40 squared to the 1/2 power. You'll notice that over on this side, 10 over 9, where the heck does that come from? Well, if I divide by 9/10, that's the same thing as multiplying by 10 over 9. That's where that 10 over 9 comes from. Then, of course, we know we're going to take a derivative of this, so that's why we have the parentheses to the 1/2 power instead of the square root symbol. So let's zoom out again and take a look at where we are now. So the next thing we're going to do is graph the function. Okay, we have a function to graph, and we can do that. A couple things to remember is that x is the leg of the triangle. Scrolling back up here, again, x is the leg of this triangle. So when x is 0, that means that we are starting from here and swimming a total of 40 meters. That's an x equals 0. We're swimming 40 meters. Here's a graph, and we have 0, f of 0. Why is that important? And we just talked about that. That's the leg of the triangle when you run the whole way. In other words, you've run the full 60 meters, and then you're going to swim the full 40 meters. The next one is 55 and f of 5. Well, what would happen when x is 55? Well, over here, if x is 55, that means that we go all the way to here, and then we swim diagonally. So basically, we've run as little as possible, and we're swimming as much as possible. So we have to run at least those 5 meters. So what is that? 55 and then f of 55. That's what happens. That's the minimum distance we can run is going to be that 5 meters. So this right over here really should say f of 55 and not f of 5. So taking a look at this graph from Desmos, we can see that the minimum here is going to be right over here. That would be the vertex of that parabola shape. And we can estimate that at about, let's see, 6.6. So that means when x is about 6 meters, in other words, we've run 54 meters, the time is going to be also about 54 seconds. So that's what we're looking for. This is going to be our optimization. We're still going to have to interpret that, and we're still going to have to do the calculus. Okay, the minimum value of x is 0, the maximum value of x is 6, the minimum value is 5, and the maximum value of x is 60. Actually, those numbers sounded wrong to me. The minimum value of x should have been 0, and the maximum value of x is going to be 55. So x has to be between 0 and 55. All right, calculus time. We know what f of x is. F of x is that funky function 10 minus 1/6x plus 10/9 of x squared plus 40 squared to the 1/2 power. Notice I'm not bothering with 40 squared, making that 1600. It doesn't really matter. It's just a constant right now. So the derivative is going to be a little bit difficult. The first part of the derivative here is the derivative of 10, which of course is nothing. The derivative of negative 1/6x. That's negative 1/6. Now, how about the derivative of 10/9 of this square root? Well, 10 over 9 is just a constant, so we can just leave that constant. And then the derivative of anything to the 1/2 power is that thing, the base of the power, to the decreased power. So here we have the base to the negative 1/2 power, because 1/2 minus 1/2 is negative 1/2. And then we're going to multiply by the old power 1/2, and then multiply again by the derivative of the base. So the derivative of x squared plus 40 squared is just 2x. And how does that simplify? Well, that's negative 1/6 plus 10 over x, 10x over 9 square root of x squared plus 40 squared. Okay, so now we're supposed to solve that. When is the derivative equal to 0? Which is a good time for us to grab our calculator. Okay, we put that derivative into y1, and we're going to set a window now. We know the minimum that x could be is 0. The maximum x could be is 55. And I'm going to keep y min and y max at negative 10 and 10. Because if you'll remember, I'm not particularly interested in the shape of the derivative. I'm interested with the derivative. When is the derivative equal to 0? So a window for y min goes to negative 10 and y max equals 10. That's going to capture any place where the derivative is equal to 0. So I'm going to push graph next. And let's see. Ooh, well, that's kind of hard to see because that derivative is sticking close to the x-axis. So what that says to me is I need to decrease this window a little bit. Instead of -10 to 10, perhaps -1 to +1 will help me, will exaggerate that vertically. Let's see what we have. Okay, negative derivatives. Well, that looks kind of odd. And you were probably yelling at me earlier because I forgot to put the x in the numerator of this fraction. Okay, well, that probably did it. Let's see if that changed things. Okay, let's graph this now. And, oh, boom, there we go. All right, so now all I have to do is find that 0. Additionally, some other information that we get from this graph is over here on the left side, we have a place where the derivative is negative. Over on the right side, let me trace this so we can see where I'm talking about. Where the cursor is right now, the derivative is positive because the y-coordinate is greater than 0. Over here on the other side of things, the derivative is negative because the cursor is below the x-axis. And right around here, right around 6.666, 6 2/3, we have ourselves a place where the derivative is 0. Let's find where that is exactly. Second, calculate a 0. We'll cursor to the left of the 0 and push enter. Then we'll cursor to the right of the 0, push enter again. Cursor over on top of the 0, push enter. And there we go, 606866. So we have this 606866. It says use a solver. I use the graphical method, of course, which is a way of solving things. But basically use some kind of something to solve this for you. That's what your calculator's for. So the next thing we're going to need to do is to solve the mathematical model, which means we're going to use the candidate test. Okay, when x is equal to 55, x equals 6066 over here. Let's go ahead and do this with the calculator the way we have been doing this. Now remember, we're substituting into that time formula, not the derivative of the time formula. So we're going to have to put the time formula in our calculator. So I've got in y2 the function, the time function, not the derivative of the time function, just the time function. Notice I kept this in the original state without any simplification. And then I'm going to go to table set, make sure that this says independent ask. Then I'm going to go to the tables, second graph, and I'm going to substitute my values. I know smallest x could be as 0. The biggest x could be as 55. And then I'm going to put my critical value there. And that gives me my 3 values, 4611, 68064, and 45608. Now a lot of you say that, well, Ferreria, if you want this to 5 decimal places, my calculator doesn't display it. And you just need to make sure that you cursor on top of those values, and the full value, untruncated, will show up right over at the bottom of the screen. So that's how you would get those full values. And it seems like I mucked this all up again. It should have been 60 minus x over here in y2. So here are the actual values that we're going to be putting into our chart, 76397. Let's scroll over so we can see the unrounded values. 5.444, 76.39705, and 53.94159. Back on our paper, we have those values in there. So this looks like it's going to be the maximum time is if x is 55, which would mean that we only ran 5 meters. That makes sense. And then this one over here, this is going to be our minimum time. So our minimum time is going to be if x is 6.06. Let's zoom out again, get a bigger picture of what's going on, and let's start answering some questions. Let's interpret the solution when x is equal to that 6.066. F of x is going to be equal to 53. Okay, so the zombie biathlon will have a minimum time, and let's remember that f of x is the minimum time, so the minimum time is going to be that 53.941. Now, if the x is 0.9, if the time is 53 and x is 6.06, how far did you run? Well, let's remember that x doesn't tell me how far I ran, x tells me how far I didn't run. So the amount that we ran is 60.60866. Let's go back to the model over here and remember that x was this distance over here. So that's the amount that we don't run. The amount that we do run is this much right over here. And that's going to be 60 minus x. And that was even written over here. What's the total distance to run? It's 60 minus x. So coming back down to our interpretation, the Zombiathlon has a minimum time when you run for, well, it turns out that you run for that 60 minus 6.06 is about 53.93. What about how far did we swim? Well, coming back up, the swimming distance was right here. What was the total distance that we swam? It's the square root of x squared plus 40 squared. So coming back down over here, how far did we swim? So if the amount that we swim is going to be the square root of 6.068 squared plus 40 squared, grabbing my calculator, that gives me the number 40.4577. So right over here, that's how far I swim. So that is our zombie biathlon. That's how far it goes. This was a very difficult problem. If you want to watch this video a couple times to get it, I wouldn't say no to you. So let's move on. Same important ideas. Once we get to more complicated problems, it's much more important for you to really understand what's going on. There'll be multiple equations at play, and a lot of them won't be a trivial equation, so you've really got to be up on it. So let's check our understanding here. You operate a service that escorts people on a dangerous trip outside of Zombieland. You won't make the trip unless 2 people have hired you. So you're going to charge the following rates. $2,000 for 1 person. For every additional person up to a maximum of 10 people, your per person rate is reduced by $173. It costs $800 plus $100 a person to make the trip. So the first thing we're going to do is part A, find an equation for R, the gross revenue. Part B, find an equation for C, the cost of the trip. And then part C here is going to be how many people will it take for you to maximize your profit. So we're going to answer parts A and B as we do this problem. So first thing, second thing really, develop a mathematical model for this problem. So we're going to say X is the number of people on the trip. Now if 1 person goes on the trip, then it's going to be $2,000 is going to be the revenue. We're going to do that first. If 2 people go on the trip, then it's going to be, what is this, 2,000 minus 173 multiplied by 2. And if 3 people go on the trip, it's going to be the quantity of 2,000 minus 2 times 173 multiplied by 3. So I'm taking that 173 and I'm subtracting it by 1 less than the number of people on the trip. So if 5 people go on the trip, I'll multiply 173 by 4. And then I'm going to multiply that number by 2,000. And then I'm going to multiply that by the number of people on the trip. Sorry, I meant to subtract that from 1,000. So here is what I'm saying. This part right over here, this is the rate. Okay, this is going to be the rate. The base rate is $2,000 a person, and we're going to subtract $173 for every additional person past the first person. So again, if this x is 2, then this is going to be 2 minus 1, or just 1. So we only discounted 173. If 5 people go on the trip, then this is going to be 4, and we're going to discount the trip by the per person price by 4 times 173. And so the trip total cost per person is going to be 2,000 minus 4 times 173. Now that's the per person rate, so we still have to multiply that by x in order to get the total cost. It's pretty complex, actually. Simplified, that's 2,173x minus 173x squared. That does it for part A. Part B, the cost equation. Well, the cost is going to be $8,000 plus $100 per person. That's a pretty easy equation, I think. So that cost is going to be 800 minus 100x. That really should be plus 100x. That makes our function for profit, which would be the r function minus the c function. That's going to be that negative 173x squared plus 2,073x minus 800. Again, that's just r minus c. So our next task here is going to be to graph the function. So let's remember that this is a discrete function. If you just drag that function into Desmos, you'll get something that looks like this. This is a discrete function, so really there are only so many values of x that work, namely 1 to 10 integer values. For the next part here, we're going to identify critical points and endpoints, and we'll do this by solving our derivative and setting that equal to 0. So starting with the derivative, with the function, we've got the function, our profit function is at negative 173x squared plus 2,073 minus 800. That makes our f prime negative 346x plus 2073. This makes our critical value 2,073 divided by 346, or 5.9913. Let's solve this mathematical model. Let's do our candidate test using our calculator. Here we've got our cost function in y1. We'll go to our tables and let's figure out our minimum was 1, our maximum was 10, and our critical value, well, that was 5.9913. But let's remember that actually this was a discrete function. So we don't have 5.99 people. We have 6 people, and we can check that against 5 people, and we can see that the maximum here profit is going to be with 6 people, and that's going to be 5,410. Bringing that back to our answer key, into our work. Because f is discrete, we're going to test the two values around the critical value. So we're going to test both 6 and 5, because 6 is greater than 5.9 and 5 is less than 5.9. And that will give us our maximum function, or our maximum profit. So let's interpret the solution now. Interpreting our solution, we have our r function is 2,173x minus 173x squared. Our c function was 800 plus 100x. And we found a maximum profit of $5,410 when 6 people are taken out of Zombieland. And that just about does it for us in our chapter 4. Typically, after chapter 4, section 4 in chapter 5, you're going to have a quiz. So if that's you this year, good luck on your quiz. And we'll see you next time here for more calculus. Have a good one.